All right, now we're going to talk about igneous rocks, and I tend to go straight into igneous rocks after minerals because igneous rocks are most directly composed of minerals. And this takes a lot of visualization, and again, this is another 14-week class in and of itself. We're doing it in 2 lectures. Okay, we're by no means even scratching the surface on what there is out there to understand, but we're doing what we have time for. So it takes a while to understand what's really going on. It's not, I always use the Lego example, right? So it's not like you're taking a white Lego, a clear Lego, and a peach-colored Lego, and a black Lego, and putting those together and saying, here, it's granite. It's not like the minerals are preformed. You're plucking them out and putting them together. It's close, but it's not like that. Instead, these things are in a pool of magma. It's an igneous rock, right? It's made out of magma or lava. So these things are in a pool of magma, and magma is made up of a whole bunch of elements. Part of the definition of a mineral is that it must be naturally occurring, inorganic, and crystalline, right? So it's not really a mineral until it's a crystal, until it has crystallized. So there's no minerals in this pool of magma. It's all just elemental stew. So what's happening is these minerals are growing out more or less at the same time. You'll see in a moment or three that there's an order to this madness. Somebody actually figured it out, sat and watched lava cool, I guess, several dozen times and realized that there is an order. But for the most part, the minerals themselves are not pre-existing and then, put together like that. So it doesn't sound like a horribly important distinction, but it is. I just added this slide a couple semesters ago. I don't know why I never made the connection, because I really love word origins. Etymology, as it's called. Not entomology, that's the study of bugs, but etymology. And I really dig that. And I don't know, somehow I never looked into igneous. It's kind of a weird word. It makes me wonder if St. Ignatius is in some way connected to fire. I don't know. But, so we see other words, ignite and ignition, coming from the same root. There we go. Isn't that beautiful? All right. That is, of course, a picture of lava. Hard to get into the earth and take pictures of magma. Magma and lava are, for all intents and purposes at this point, they are the same thing, except when it's at the surface, we call it one thing, and when it's inside the earth, we call it something else. There's hugely different pressures and temperatures associated with being at the inside the earth as opposed to at the surface. So property-wise, they're completely different critters. But essentially, again, they're just molten mineral elemental mixtures. So igneous rocks, again, this is sort of retelling you, but igneous rocks are made from mineral crystals that grow in cooling magma or lava. And they do this in one of 2 places. At the surface of the earth or inside the earth, which I just told you. So this molten mineral mixture is composed of elements. I've said that already. And we call it magma or lava. We've talked about that. magma when it's inside of the earth, and lava when it is at the surface of the earth. Whether or not you're inside the earth or at the surface of the earth, we have a different word to use. Inside and outside was too simple for them, I guess. You've probably heard these words before, intrusive and extrusive, as types of igneous rocks. All right? So intrusive, inside. Try to remember that connection there, the in and the in. So they crystallize inside the earth, therefore they grow in magma, not lava. Because they're inside the earth, they are insulated. All right? And this is something that doesn't get a whole lot of use. I don't know why. I think it's mainly because of the shape. But that cooler that you use to cool all of your favorite beverages could also be used as a warmer, so to speak, an insulator, right? If it's insulating enough to keep ice solid and your beverage is cold, it's also insulated enough to keep heat in. So in just that way, the earth keeps this magma warmer a lot longer than lava stays warm at the surface. As such, the minerals can take a lot more time growing. And because they can do that, they tend to get much larger than the mineral grains do that grow at the surface. So this goes back to what you may have learned in earth science in high school, that intrusive igneous rocks have what we call coarse grains, larger grain crystals, than do the extrusive, the other, I haven't used that word yet, but the outside rocks. So intrusive igneous rocks, inside, coarse-grained or large-grained. Now, we're in college now, so we're going to use a new word, all right? Presumably new. Phaneritic. That's the real word. That's what your textbook says. I believe I introduced it into the lab book finally. I never used them. Again, you guys have enough vocabulary out there. If we could get by with saying coarse and fine, which are words you already know, I see no reason. But they're here. I'm presenting them to you. Phanero as a prefix means visible. If you studied fossils at all, you know that most of the last several hundred million years are in something called the Phanerozoic era. Zo, we've got a zo down the street, right? Zoa means life. Phanero means visible, so it's visible life. Phanero is the prefix. So phaneritic just means visible grains, and you will be able to see, and that's what you're going to do in lab when we get there. You say, oh, this one has big crystals. I can see that. It must be intrusive. The other word, and I really don't use this one, all right, but again, some of the textbooks do, is plutonic rocks. All right, plutons are giant pools of magma, named after Pluto, the god of the underworld, not the dog. But yeah, that's where that one comes from. Like I said, I really don't use that, but you'll see it here and there. Phaneritic, I'm trying to start using, and you'll see its corollary here in a moment. Aphanitic, A again means not. So they're going for visible and not visible, which is kind of cool. But coarse-grained is totally fine by me. And look, you can see different colors. The simple fact that you can see the different colors tells you that the crystals are big enough that your eye doesn't blur them all into one. Remember we talked about printers so lovingly a couple minutes ago. You got all of what, 3 color tanks in there, not counting black? Yet it could make, in theory, any color on the planet. How does it do that? Well, it puts tiny little dots so close together that your eye can't pick them apart. And it looks like a certain shade, right? The fine grains end up doing just that. The rock is going to be more or less solid colored. But when you see the variation like this, more than likely you've got a a coarse-grained, you've got an intrusive igneous rock in front of you. Don't worry about the felsic intermediate mafic. We will get there. Don't you fret. This is mainly for crystals. Extrusive. External, extrude, whatever. Extraterrestrial, not from the earth. All right, that ext means something. So please don't let these be two questions that you miss on the test. Internal, intrusive, and extrusive, okay? Internal, exterior. You know these words already. We don't have magma at the surface, as we said. We've got lava at the surface. And lava, as I indicated a couple slides back, cools much more quickly than magma does. Lava tends to cool within a couple days to sometimes a week or so, compared to, thousands of years often for the other stuff. You'd think for the time difference it would be a lot more significant crystal change, but they must grow really slow. So anyhow, as such, they don't have a whole lot of time to grow before it cools. Think of it as like cabbages growing in your garden, okay? The longer you leave them there, the bigger they're going to get. If they stop growing really, really, really quickly, they're not going to be that big. And why do they stop growing? Just in case this isn't clear, it's because the material cooled off. Okay, it hardened. It stays liquid, molten, longer inside the earth. All right, anywho. So to go back to those terms, aphanitic. A means not, fan is still visible, so not visible. These are your fine-grained igneous rocks. And sometimes I say volcanic rocks. If it's not obvious at this point, lava comes out of volcanoes, which is why they call them volcanic rocks. I mainly say intrusive and extrusive, personally. Okay. I don't think phanero and aphanitic made it to test questions. Remind me before the test and I'll check. I think we keep it at intrusive and extrusive. And there is a bunch of questions about this. It really seems like I'm beating a dead horse, but I want you guys to understand intrusive, extrusive, lava, magma, coarse-grained, fine-grained. It's, what is that, 6 things? That's 6 questions. Okay? Should be straightforward questions for you, but if you forget to review it, it might not be. So these, as I said, are much more uniform in color. Yeah, there's always going to be a sparkle or a speckle of this, that, or the other thing. But arguably speaking, they're much more uniform in color. And these just happen to be 3 that you're going to, 3 intrusive igneous rocks that you're going to see. We only look at 9 igneous rocks. It's a huge shock from you guys when you come off of minerals where we had practically 3 dozen. And we come into rocks, and we tend to average around a dozen. Metamorphics are really low. Seds are a little high. Sedimentaries. Igneous is right in the middle. All right, but you got to add all those together for the rock test, and then you're back up to 30-something. So, yes, sir, question.
What are felsic intermediate?
Like I said, we'll get there. We're talking about crystal structure now. That's chemical composition, and we'll get there in the second half of the slide. It was on the previous slide as well, or second half of the presentation. It was on the previous slide as well, if you might recall. Oops, I'm going the wrong way. See, they're there too. But we'll get there. Okay. We got one more. Remember I told you that they either cool at the surface or inside the earth? Well, there's one case where they can start cooling inside and finish outside. And that's these guys. Porphyritic. Porphyrs are large isolated crystals, so to speak. So what happens, again, we haven't gotten to that slide yet, but I told you there was a gentleman who said that there is a predictable pattern in which these materials grow out of a cooling lava or magma, right? They don't all grow at the same time. So arguably, as your pool of magma starts to cool off, inside the earth, or even at the surface with lava, something has to grow first. All right? And what ends up happening is for some reason or another, it's not pure chance. There's a handful of reasons that set up this phenomena. But the material starts to cool inside the earth, and for whatever reason, it gets caught up in a volcanic activity of some sort, and it finishes cooling at the surface. So you've got some crystals that have started to grow. Picture raisins in pudding. Kind of a gross thing, okay? But picture raisins in pudding. So you've got some crystals that are already there. This comes to the surface as lava. The majority of the rock cools as a fine-grained rock because it's at the surface, but you've got these big guys that already grew floating around in it. We call it the chocolate chip cookie rock, okay? Because I don't like raisins in pudding. Technically speaking, it is a fine-grained matrix with large crystals or porphyrs. Matrix, just like the movie, it's the background, okay? So when they say matrix, they're talking about the majority of the rock. So a fine-grained rock with large crystals in it, and it looks a little something like that. That happens to look exactly like what we have in lab. But that is not, I cited it, so that is not mine apparently. So porphyritic. So we've got, well, I have a summary slide. All right, so when we talk about classifying igneous rocks, which is what this is all leading up to, all right, we have two primary criteria. Texture, which is the grain size that we've been talking about, and the mineralogical composition, what they're made up of, their chemistry, if you would. And we've yet to talk about that. And I do believe I have a summary slide for texture. Okay, so before we leave and move on to the mineralogical stuff, so we have the phaneritics, the aphenitics, and the porphyritics that we've talked about. Phaneritics were coarse-grained. These were the intrusive guys. Aphenitics are your fine-grained. These are the extrusive guys. We've got porphyritic, which was a mixture of intrusive and extrusive. A hybrid, if you would. And then there's two that we haven't talked about yet. Vesicular and glassy. So we've got our coarse, fine, and our mixed right up there across the top. Our phaneritic, our aphanitic, and our porphyritic. If I recall, this isn't the best picture. Those dark spots there are holes. A vesicle is a pocket, if you would. Yes, sir.
Is that pumice?
No. But pumice is vesicular.
Okay, good guess.
So, vesicles are holes. So vesicular rock is full of holes. Pumice is a great example. This happens to be scoria. It's the other chemistry. Vesicular rocks, lava, and volcanoes, you might know, are chock full of gases. All right? And under pressure, that gas is quite happily in dissolved, we'll just say. All right? But once it comes out to the surface, it's allowed to bubble out through. A lot like when you pour yourself a glass of a carbonated beverage. Okay, you get that foam or the head on top. This is exactly that, except instead of just kind of dissipating, it cools and leaves a structure behind forever. So scoria and pumice are, you could think of them as the foam that rises to the top of a couple different lavas. Okay, so they're called vesicular because they have vesicles. Glassy, and these really deserve the larger pictures. I think I will do this in time ahead, but you'll see them in lab. You'll see them. Glassy is, well, just that. It's glassy. Everyone probably has seen a piece of obsidian, okay? Volcanic glass. Black, smooth, sharp. This is a nice picture. It's got some different colors in it. Obsidian can be more than just black. There's brown, there's red. There's often some gray in it because there's some ash mixed in. Now, going back to our sort of hierarchy that we were making with intrusive, extrusive, and mixed, these guys fall under extrusive because they grow out of lava, so to speak. All right. When we look at them in lab, they don't show up in the table where we just showed you. You probably didn't remember the names, but you saw like granite, rhyolite, diorite, gabbro, a handful of other things, basalt. Those are crystalline igneous rocks. These guys, they don't form a crystal structure. So they don't show up in the mineral identification tables. You always have them in a little separate thing. But they are essentially extrusive because they form at the surface. All right. I think that we will call, what time do we go to? Like 11 on the nose?
Yeah.
So it's not after 11. I think before, because I cannot finish this in 15 minutes, I don't think. So I don't want to end up doing like all but 4 slides and leave that for next time and end up making a 3-minute recording, so on and so forth. So even though it is a little early, it's not that early. I'll take attendance really slow. We will start the mineralogy of igneous rocks after this, in the next class. Then we're going on to volcanoes. Volcanoes takes a handful of lectures. And believe it or not, after volcanoes, we're actually looking at test 2. Okay? Might seem kind of sudden, but that's actually all the better. Get stuff in and out. I told you roughly every 3 to 4 PowerPoints we have a lecture. A test. And volcanoes is, if this hasn't been enough vocabulary for you, believe me, volcanoes is very vocabulary intensive. So certainly plenty of content. Even if time-wise it might come a little quicker after test 1 than you were hoping. All right.